All right, welcome everybody. Today we're going to talk about Calc Lesson number 38, and this is all about analytical and graphical connections between the original function f, the first derivative, and the second derivative. Technically speaking, everything on this first page of notes you already know. But we want to be able to kind of put all the information in one spot, nice and organized. And then most importantly, we want to be able to make connections, not just algebraically between the first derivative, the second derivative, and the original function, but graphically. In a lot of ways, your ability to make the graphical connections is both the most important and the hardest part. If you do have any kind of highlighters or colored pencils or markers, you're definitely going to want them for the second two pages. So just something to keep in mind here. So we're starting off by comparing what we know about the first derivative to what that tells us about the original f. So just pay careful attention to the notation here. Again, technically, everything in this table, we already know about the relationship between the first derivative and the original, but we do want to write it formally just to make sure that there is no confusion. So if the first derivative on the left-hand side is equal to 0 or is undefined at a specific value x equals a, remember those are the critical numbers, then what does it tell us about the original function f? It tells us that there is a potential, and again, potential relative max or min we say potential because you're only possibly going to have a relative max or min for the places where it's equal to 0. But again, in terms of critical numbers, those are the only places where the relative maxes and mins can occur. If it turns out that the first derivative is greater than 0, which means it's positive, that of course tells us where the original function is increasing. Whereas if it's negative or less than 0, that of course tells us where the original function is decreasing. If when you're finding increasing and decreasing, you do your sign test and you test the positivity and the negativity. If it changes from a positive to a negative, that tells us that there has to be a relative max there. And if it changes from a negative to a positive, then that tells us that there is a relative min there. Again, remember, in the first row, we're just talking about potential relative maxes and mins. You would actually have to do the sign test in order to say for sure that there was a relative max or min. And again, that's what the first derivative test tells us. You guys have been doing that for days now, but just to kind of write it all in one spot, you want to make sure that you not only can do it with just numbers and algebraically, but that you can also explain and try to be able to interpret those relationships. So a little more as we go down the page here. So again, a reminder, the first derivative identifies the intervals where the original is increasing, decrease, and has a relative max or min. The second derivative identifies spots on the original where it's concave up, concave down, or has a point of inflection. Something, again, that we've kind of been talking about, but we want to make sure is absolutely clear. Since the second derivative is the first derivative of f prime, then whatever the relationship is between the original and the first derivative also has to exist between the first and second derivative. So if you stop and think about that for a second, it should make sense. Might kind of seem like a mouthful, but let's go ahead and formalize that relationship just so that we're absolutely clear. So again, pay close attention here to the notation. On the absolute left, we are talking about the second derivative. In the middle, we're talking about the original function. And then all the way to the right, we're talking about the first derivative. So again, it's never going to be a secret what notation we're talking about, but we want to make sure that you know exactly what you're looking at. So over to the absolute left, if the second derivative is equal to 0 or undefined, again, those are the critical numbers, then we say that the original has a potential point of inflection. We emphasize again, potential point of inflection. We wouldn't know for sure until we actually tested it. If the second derivative is greater than 0, then that tells us where the original is concave up. Whereas if it's negative, it tells us where the original is concave down. Then, if it changes from a positive to a negative, or from a negative to a positive, it doesn't matter which one, then we can say for sure that there is a point of inflection there. Again, in the first row there, it's just potentially a point of inflection. We'd have to know for sure by doing the test. So again, you know what the second derivative tells you about the original. That's the second derivative test. What you also now have to realize is that because the second derivative is the derivative of the first derivative, whatever the relationship is between the first derivative and the original also has to be true between the second derivative and the first derivative. So going back to the left-hand side of the table, if the second derivative is equal to 0 or undefined at the critical numbers, that tells us that the first derivative has a potential relative min or max. And again, only ever potentially. You'd have to test to know for sure. Wherever the second derivative is positive, that tells us where the first derivative is increasing. Tells us where, if it's negative, that it's decreasing. If it changes from a positive to a negative, then we know for sure that there has to be a relative maximum there. And if it changes from a negative to a positive, then we know there has to be a relative minimum there. So I would imagine, half of you are going to be absolutely okay with this. You totally understand that every time you take a derivative, whatever that relationship is to the previous level has to remain the same. Maybe some of you are like, there's too much notation here. I can't really keep it straight. That's exactly why we put it all on this page, one-stop shopping. Having it all organized is really going to be super helpful for the next couple of lessons. The next couple of lessons specifically asked you to relate and analyze how the graph of an original relates to the graph of the first derivative, to the second derivative, and then ultimately how to create graphs, not from equations, but instead from analytical data. So again, in some ways, the hardest thing we've done so far, which is why we've kind of left it till the end. So taking a look at the next page here, and again, if you did have any colors, this might be where you want to, have them handy, as I am going to use quite a lot of them. So let's kind of go look through here just one at a time. First of all, I have for you 4 different boxes, 3 different graphs, and then in the final box, I put them all together. So we're assuming that the original function here, f, is 2x squared minus 8. That is a quadratic that faces up with a y-intercept of -8 and x-intercepts of 2 and -2. If you were to take the derivative algebraically, you would get 4x, which is linear, which is shown there in blue, through the origin with a positive slope of 4. If you were to take the derivative of that, the second derivative would simply be 4, which is a constant, so it goes from left to right at y equals 4. And then in the final box, it just shows you all 3 graphs on the same axes. Some people find it easier to have them all on the same axes, where some people prefer to have them separately. So I wanted to show you all the different combinations. Okay, so on the previous page, we wrote in words what the relationship was among the first, second, and original function. Now we're going to go ahead and show them graphically. So we're going to go ahead and start with the second derivative. What I want to point out here about the second derivative, and again, if you're going to color code, then you're going to go ahead and follow my lead here. So as we take a look at the second derivative, what we want to note here is that it's always positive. So +4, +4, +4, we want to note here that the second derivative is always positive. What does the second derivative being positive tell us about the original? Well, it tells us that the entire original should be concave up. And if you were to look here, the entire graph from -infinity to infinity does in fact appear to be concave up. So that is the graphical relationship between the second derivative and the original. Anywhere that the second derivative is positive, that tells us where the original graph is concave up. Then we also want to consider what is the relationship between the second derivative and the first derivative. So if the second derivative, again, is all positive, what the second derivative being positive is supposed to tell us about the first derivative is where it is increasing. And if you go back to the graph of the first derivative, you should hopefully agree that the entirety of the graph from negative infinity to infinity is, of course, increasing. So everything is in yellow, showing you the relationship, one from the second derivative to the original function, and then again from the second derivative to the first derivative. So at this time, we have used everything we know about the second derivative. So now we're going to look at the first derivative. So what does the first derivative tell us about the original? Well, if we locate the region on the first derivative that is positive, notice that's from 0 to infinity. That is supposed to tell us on the original where the graph is increasing. And if you were to go back here and take a look from 0 to infinity, hopefully you would agree that that is where the graph is increasing. Then if you were to go back to the first derivative, and if you were to locate the region where the graph is negative, what is the first derivative being negative supposed to tell us about the original? Well, it's supposed to tell us where it is decreasing. And I think that if you look at that, you will see that it tracks. So again, a lot of colors going on here. Hopefully it helps. You're going to get a ton more examples, a ton more opportunities to practice this, but we did just want to, give you as many different examples as possible. If you go ahead and take a look at the final box, again, it just shows you where all the X values match up. So maybe you find it easier to look there, maybe you find it harder, but we certainly did want to give you all of those options. Let's try another one. Again, we're going to be using 3 different graphs, first independently, and then they're all together on the final slide there. A little bit more complicated. So we started off in the first box with a negative x cubed plus 9x. So this is, of course, a polynomial, a nice smooth curve. The end behavior is up, down. Take the derivative, you get negative 3x squared plus 9, which is, of course, a quadratic that faces down. And then take the derivative again, and you're going to go ahead and get a linear function of negative 6x. So again, as we go through, we're going to first analyze what does the second derivative tell us about the original, then what does the second derivative tell us about the first, and then ultimately what does the first tell us about the original. So taking all those words from the first page and now translating them to a graph. So starting with the second derivative, the first thing that I'm going to point out here for the second derivative is I'm going to point out where the second derivative is positive. So the second derivative is positive here. What is the second derivative being positive supposed to tell us about the original function? Well, it is supposed to tell us where the original function is concave up. So here it's from negative infinity to 0, which means that on the original graph, it should track. And it does. And again, this is where it's concave up. Going back to the second derivative, we now want to locate the regions where the second derivative is negative. What is the second derivative being negative? So 0 to infinity, supposed to tell us about the original. It's supposed to tell us where the original is concave down. And would you look at that, from 0 to infinity, looks like we would agree that that is, in fact, concave down. So again, that's everything that the second derivative tells us about the original. Now we're going to go ahead and take a look at the first derivative. So taking a look at the first derivative, we're first going to take a look at the regions where the first derivative is positive. So the first derivative is positive here at this location. What is that supposed to tell us about the original? Well, that's supposed to tell us where it is increasing. So if you take a look at the axis, it's a little bit past -1, and then all the way up to a little bit past +1. And I think if you were to highlight that same region on the original, you would hopefully agree that that pink is where the original graph is increasing. Again, I know there's a lot of colors. I'm not really 100% sure on a better way to do this. So then you're going to go ahead and indicate on the first derivative the locations where it is negative. What are the values on the first derivative being negative supposed to tell us about the original function? Well, that's supposed to tell us the spot where the original function is decreasing. So it's from negative infinity to negative 1.5-ish, which is here. And then it's from positive 1.5-ish to positive infinity. And again, that's supposed to tell us where the graph is decreasing in yellow. So everything that the second derivative tells us about the original, everything that the first derivative tells us about the original, the final step is what are the other things that the second derivative tells us about the first derivative. So if I go back to the second derivative and I again highlight the region where the second derivative is positive, that is supposed to tell me on the graph of the first derivative where the graph is increasing. And I think that if we did that, you would see that it works. Then if you were to go back to the second derivative and identify again the spots where it is negative, that is supposed to tell us where the first derivative is decreasing, which again, hopefully you would agree that that is in fact the case. One final thing I want to point out, if you were to go to the second derivative, and if you were to highlight the x-intercept, which would be at x equals 0, if you were to take a look at the first derivative, that would tell us that at x equals 0, that is where we have a relative maximum. And then if you were to go to the original at x equals 0, that is where you would have your point of inflection. So again, it actually is awesome that it all winds up working out quite the way that it does. Maybe you're not into it enough to understand the beauty of the relationship, but it certainly is there. And then again, all three graphs are kind of put together there on the final spot if you like looking at them all at one time, although we know it gets a little bit crowded. All right, so what I have for you now, this is a website which your teacher is going to share with you later today, and it allows you the chance to try to match the graphs of some functions with their first derivatives. Now, the ultimate goal here is for you to be able to match not only an original to the first derivative and to the second derivative, which you're going to get a chance to do. In the past, all of these matching activities would have been done in person in groups and using pen and paper. It's a little bit hard to do it digitally, so we're kind of limited in the resources, but this is kind of a good one. So basically, it will constantly reload for you 4 new graphs and then 4 potential first derivatives, and you're going to try to match them up by moving one of these bottom 4 graphs, which are your derivative choices, underneath the corresponding function graphs, and that will tell you if you're right or not. So here's the thing. When you're trying to match these, you have a couple of different things that you're looking at. Sometimes, depending on the functions in question, you can try to match them simply using what you know about their degrees and about their shapes. So for example, if you were to take a look at these 4 original function graphs, the one that stands out the most to me is this linear function over here on the right. If I know that my graph is a linear and I take the derivative, the only way that that can happen is if it's a constant. Of these 4 first derivative choices, there's only one that's a constant, so I'm pretty confident that that is going to match up there. And look at that, it tells me that it's true. Again, think about what the relationship is supposed to be analytically. Wherever this function graph is positive is supposed to be where the original graph is increasing. Because of the fact that the entire first derivative is positive, it means that the entire graph of the function should be increasing. So crushed it. Then the next one that jumps out at me, at least in terms of trying to do this matching, is this upside down quadratic. If I was to take the derivative of a negative quadratic, I would get a negative linear, which I believe has to be this one. Look at that, another true. If you're trying to think about analytically what's supposed to be true, wherever the first derivative graph is positive is where the original graph is supposed to be increasing. Wherever the first derivative graph is negative is supposed to be where the original graph is decreasing. So again, sometimes you can just use what the shapes of the functions are, and then obviously for functions that look a little different, you're not really going to be able to do that. So again, I look at this function on the absolute left and I see an upside down quartic. The derivative of a negative quartic would be a negative cubic, which I think has to be this one here. Again, taking a look, a little harder here since there's more going on. So wherever this graph is positive, the first derivative is where the original should be increasing. Wherever the first derivative is negative is where the original graph should be decreasing. Positive means increasing and negative means decreasing. Really, the best thing about this site is that it matches up the numbers exactly so that you can see clearly wherever there's a change in the original, there's a change in the first derivative. Then let's say you were trying to match something like this second graph here. Well, that's not really a graph that I am familiar with. So obviously, process of elimination, I know that it has to match, but let's make sure we understand why. Because of the fact that you have, this really small value over here and you have this really small value over here, it looks like it's barely positive, which means this should kind of be barely increasing. So it's a little hard to tell. Then you can see again that it's positive and you can see that that's where it's increasing. Then your negative regions is where this graph is decreasing. And then finally, your positive region again is where it is increasing. And then again, these really small values, it's a little bit harder to tell what's going on. But if these were your only 4 choices, you could feel absolutely confident that these were correct. Let's go ahead and try another set. So if I were to evaluate myself, I got a 10 out of 10, obviously. And then you can go ahead and click Load New. And it's now going to give you 4 different graphs. So let's go ahead and do one more set. And then again, depending on the timing of your class, your teacher might have you do some on your own or maybe assign some for homework, or you can always just go back and do these for funsies. So again, taking a look at these 4 graphs, we're going to use not only what we know about the shapes, but also what we know about just the behaviors. So looking at this positive linear graph, the derivative of which has to be a positive constant. Because the first derivative is all positive, that means that the graph should be all increasing. Then I see this positive quadratic, the derivative of which would be a positive linear. Again, take a look at where the graph is positive, starting at approximately negative 1.5-ish is where the original graph should be increasing. Again, starting at approximately negative 1.5-ish, and then the negative corresponds to the decreasing. Let's say that there had been another row underneath of second derivative graphs. You would then have 2 options. You can try to match the second derivative graph to the first derivative using the positive, negative, and increasing and decreasing. You can also further confirm by trying to match the second derivative to the original by looking at the positive concave up and then the negative concave down. And again, putting this all together is what you're ultimately going to get a chance to do in your groups soon. Taking a look at the ones that are left, the one on the far right looks like a negative quartic to me, the derivative of which would be a negative cubic. So this positive region would imply an increase. This negative region would imply a decrease. Then positive, another increase, and then negative, another decrease. Finally, the original looks like a positive quintic polynomial, the derivative of which would be a positive quartic. And again, the more curves there are, the more turning points. It's a little harder to see, but I promise it works. Here's my positive. Here's my increasing. Here's my negative. Here's my decreasing. Here's my positive and my increase. Here's my negative and my decrease, and then my positive and my increase. Evaluate my score again. Oh, look at that, another 10 out of 10. So I would recommend going to this website, click Load New. It's going to give you a couple of different options. All right, and last but not least, let's say we did ask you to match not only the original function graph f, but also to its first and second derivative. The easiest way to do that we have found over the years is that you would put them in order, like I've shown you here, 3 in a row, starting with the original function at the top. which would mean that your first derivative would be underneath it and your second derivative would be underneath that. Now, in a perfect world, you have exactly the same dimensions of each one. As you can see for each of these three graphs, the x values goes from about -10 to 10, and then the y values from -7 to +7. So when you have those exact same windows, it's a lot easier to see what the relationships are. So again, a couple of different ways to look at this. If you take a look at this original function here, I don't know about you, but that's looking a little bit like the sine wave to me. We don't know exactly if it is, but it looks something like a sine wave. Well, what's the derivative of a positive sine? Well, if you're thinking it's a positive cosine, you're right. And I would say that that looks like a positive cosine. What's the derivative of a positive cosine? Well, it's actually a negative sine. So again, that is always going to be something you have in your back pocket, trying to match up the graphs just based on what their actual derivative should be. And then the other way to match them is the same way that we did with the colors at the beginning. You're trying to figure out the increasing, the decreasing, the concavity, etc. So let's go ahead and start actually with the second derivative. So if I start with the second derivative, notice that wherever the second derivative is negative, which looks like it's between 0 and 3, that should be where the first derivative is decreasing, which hopefully you would agree, it's between 0 and 3. And that should be where the original graph is concave down, which would you look at that, between 0 and 3. Then if you take a look at where the second derivative is positive, that's supposed to be where the first derivative is increasing. And that's supposed to be where the original function is concave up. So hopefully you would agree that in all these instances that it matches up exactly. I know it's a little harder to do in a group and a little bit harder to do when you have to, kind of move around the pictures themselves. But assuming that you knew which was the original graph to start, which we will tell you, you're going to try to come up with some strategy for how you would then match it in terms of the original, the first derivative, and the second derivative. One final set of 3. So again, take a look here. We have some polynomial functions. Take a look at how they're all kind of, squeezed pretty close to the y-axis. So they're all, a little bit skinny. So that's kind of a good sign. Again, take a look at the fact that the scales are all the same, which makes it a little bit easier to interpret. Again, we know that this is going to be f prime, and f double prime. Again, I already matched these for you. You will ultimately soon have to do them for yourself. Taking a look at the original graph, to me, that looks like a positive 1, 2, 3, 4, 5 quintic. So we're looking at something that would be a positive x to the 5th, the derivative of which would be a positive x to the 4th, and the derivative of which would be a positive x to the 3rd. We would not actually ask you to find those equations. I mean, we could, but we won't. So then one final time, making sure we see the connections. And again, I'm only using part of the graph. The entire graph should match up, but as soon as you know you have a match, that's really, good enough. So here we have a negative portion of the graph that should match up to where the first derivative graph is decreasing, should match up to where the original graph is concave down. Then, looking at the second derivative where it's positive, that should be matching up to where the first derivative graph is increasing to where the original graph is concave up. Remember, in terms of where the point of inflection is, you're kind of estimating a little bit, although we know that if we find the x-intercept, which the x-intercept of the second derivative looks to be just shy of 2, which means that the relative minimum of the first derivative has to be just shy of 2, which means the point of inflection has to be just shy of 2. So everything matches up exactly. This, again, is the ultimate goal, your ability to match up these graphs and their derivatives. So we're going to get a chance to practice a bunch of those soon. So thanks very much for tuning in, guys, and we will catch you next time.